Thank you very much, everyone, for attending this event. I really appreciate the invite to participate, and I'm really honored to be able to tell you a little bit about this work on declarative machine learning systems that me and Professor Chris Reff from Stanford published recently on ACMQ. This work is a statement paper, is like an opinion piece, if you want, more than a technical piece. And what we will cover is what we believe the future of machine learning systems could look like, and describe some systems that we built that go in that direction. Those systems are Overton and Ludwig, and also give a little bit of a background on how we got to these systems by analyzing the past of history of machine learning systems. Let's get started. So recently, machine learning has been a lot in the news. There's been a lot of successes in the real world adoption of machine learning. And some of those are like impact everybody's life to a certain extent. Like movie recommendation of assistants became household appliances and names in recent years. But also there's been real world application of computer vision, like for instance in agriculture, that are really effective and useful. At the same time, the recent progresses in the application of machine learning to natural sciences has been very exciting, in particular with the successes of AlphaFold from DeepMind. And the recipe for getting to this level of success has been a combination of new massively parallel hardware, GPUs, TPUs, and other kinds of accelerators, together with improvements in data infrastructure, which allowed for storing much more data, which is needed by these new models for being able to perform really well, and also by algorithmic improvements. This is something which is not super always acknowledged, to be honest, but there have been new architectures and new methodologies that allowed for improved performance also on the algorithmic level. And so our belief is that what we are observing right now is just the tip of the iceberg, really, because today machine learning is still mostly in the hand of experts. And the skill sets that are needed for developing machine learning systems are really rare still. And finally, managing and developing a machine learning system is very expensive, both in terms of time, of people that develop these systems, and also the data that goes into these systems. And so we believe that the next generation of machine learning system will actually widen the adoption of machine learning. It will lower the barrier of entry for people that are not experts in machine learning or statistics. In particular, we believe that it will not require people to write code in order to be able to train and use machine learning models. And this can be achieved by higher level of abstractions. So more abstract models and more abstract systems will enable this lower barrier of entry. We believe that declarative interfaces are really well suited for this next generation of machine learning systems, in particular because they merge the flexibility of low-level APIs and systems like TensorFlow and PyTorch with the simplicity of configuration-based systems like interfaces and AutoML. So declarative machine learning systems live at the intersection of these two worlds. And this higher level of abstraction and separation of interests is one point that we will double down in the rest of the presentation. In particular, it allows to separate the what from the how. And the what part of it can be basically declared with a configuration. And this allows for low or no or zero code, whatever you want to call it. Moreover, we believe that there's not a huge compromise that one has to pay in order to be able to use these declarative systems, because they can still achieve state-of-the-art performance. And we will show you an example with both Overton and Ludwig that are really, really performant. But let's do one step back and let's think about how we got to the point where we decided to try to implement systems that are more declarative in nature. In particular, and I'm talking about mid-2000s, early 2010s, most of the machine learning projects were really bespoke, and in many cases were not really following software engineering best practices, and that led to a lot of technical debt. And moreover, those systems took several years to be developed. Over the course of the 2010s, common patterns among these systems emerged and were encapsulated and crystallized inside libraries like scikit-learn, TensorFlow, and PyTorch. And that moved the needle from several years of development for a machine learning project to several months. And that was a great improvement, but we think we can do even better in the future. In particular, we believe that there is this inverse relationship between the complexity of the system and the interface that the user need to use and the potential adoption of that system. We have examples throughout the history of computing, for instance, compilers and databases. In the graph on the right, we show some, it's a cartoon really, but it shows an example of what we believe the relationship to be. So for instance, if you look at databases, in the 70s, if you wanted to query a database, you had to write a program in COBOL, while after the introduction of database management systems and SQL, now there's a substantially higher number of people that are capable of writing the SQL query than writing COBOL programs. And moreover, this hides the complexity of the data storage, of the indexing, and the retrieval behind the declarative query interface. Something similar happened also in game engines with higher level languages and compilers adopted for developing video games, from writing them in assembly in the 80s to writing them in C and C++ in the 90s and C# in 2010s, and now with higher order systems like Unity and the Real Engine that makes it much more easier for a much broader audience to be able to develop video games. And I think something similar has happened in machine learning too, where in the 2000s you had to write your own low-level CUDA code. Then TensorFlow and PyTorch allowed for a much simpler way to write your own machine learning models. And tools like Ludwig and Overton allow for even a simpler, higher level abstraction that allows for potentially more users, although they are much smaller projects than TensorFlow and PyTorch. So the number of users is not exactly comparable, but a potentially wider range of users to be able to use the systems. There's still in the top right that question mark that is, what is the next level of machine learning systems that allows for higher level abstraction and lower the complexity and increase the adoption. The reason why we care so much about the separation of interest is because in basically any software system and tool, there is this separation between the interface that less expert users use and that they don't need to know about the details of the implementation, and what actually expert users or developers do at the low level, which is improving the implementation by keeping the interface constant. And there's many examples of that. Database management system is an example of that, where data analysts can declare their needs in SQL, and they don't need to know about the infrastructure behind the scenes that provides them with the answers. Database admin and the developer, on the other hand, they optimize indices, they optimize the infrastructure, the query planner parameters, and so on. And for compilers, it's similar. A programmer writes high-level code in a higher-level language. They don't need to know about the assembly implementation underneath. And the compiler developer actually optimizes the parser, the heuristics for generating the assembly code, and so on. And we believe that the next generation of ML systems will have this notion of a predictive analyst, if you want, that will be able to declare the schema of the data and the task, and they don't need to know about all the underlying machine learning details. while data scientists and machine learning engineers will have their job organizing all the, let me repeat this part. While data scientists and machine learning engineers will spend time optimizing models, figuring out the architectures, the upper parameter, and the making sure that the inference of these models is very fast. The current ML platforms support this life cycle of ML models, which it's divided in several steps, from business need identification to the data exploration, collection, pipeline building, and finally deployment and monitoring. And they do it by encapsulating good practices. But most of them are mostly monolithic. They tend to become single points of failures in organizations. They also struggle to keep up with new developments, and often they also black boxes. And for instance, some AutoML solutions are like that. We believe that bridging the gap between the history of declarative interfaces with data-first systems and the model-first system is the way to go, and what we actually did with Ludwig and Overton. But let's talk in detail about the data-first systems, because systems like Oracle Data Miner, Bismarck, Madlib, Google BigQuery ML, and SQL Flow more recently, they have the advantage of integrating ML into the database and providing a declarative interface which solves the data piping problem. But the disadvantage is that usually they provide the users with a low degree of control, which creates problems with building models like featureization and model tuning. On the other hand, the model-first libraries like TensorFlow, PyTorch give total flexibility in model building and training, but require ML experts and engineers to build pipelines. And so Ludwig and Overton, as I was saying before, try to bridge this gap. While designing Ludwig and Overton, we're trying to address some challenges with some desiderata. Both of systems don't solve all these challenges, but we think it's valuable to discuss through these challenges so that future systems can try to address all of them. In particular, one challenge that we face is the exponential decision explosion. In particular, if we provide a system with many configuration parameters, the choices that the users need to do are a lot. And so our solution for that was a combination of good defaults and automation, like hyperparameter optimization and AutoML techniques. We also wanted to solve the new modelitis, which is a term that Chris coined, which is basically the illness of machine learning organizations that need to create new modular architectures every single time, while we provide with standardized implementation of, and that are focused on quality of both the implementation and the data that is used as a way around the need to implement new models every single time. Another challenge that we faced was the amount of chasms that are there in organizations that try to build machine learning projects, and the handoff that needs to happen between these organizations. And so we solve that by providing common interfaces that can both parts of the both people on the both sides of the chasm can understand. The scarcity of expertise, we already touched upon it, but it's still an issue because not many people trained in machine learning, statistics, and data science are available on the market. And so we think that with this higher level abstraction that we're providing, we are partially solving this issue. We also wanted to solve the issue of slow development process. And so we want to enable rapid iteration through our systems. And finally, the fact that many diverse stakeholders, engineers, analysts, data scientists, data engineers, machine learning people are all involved usually in the development of a machine learning project. With the separation of interest, we try to address this issue too. Let's double down on looking exactly at what Overton and Ludwig are and what they did, so that it could hopefully be of inspiration for a next generation of systems. Overton was a system developed at Apple internally between the 2018 and 2019, 19, really. And it was responsible for massive gains in quality where it was adopted, in particular between 40 and 82% error reduction on search and question answering applications. It worked by providing a configuration system. You can see an example on the right, but we will expand on that in a minute to give more details. And the nice thing about it is that this configuration system allowed so that Overton users changed their roles and focused much more time on monitoring performance of the systems, improving supervision, and providing new types of supervision without the need to write models in low-level machine learning code. So how did Overton achieve that? You can see here the distinction between an example of a data record and how the schema that is provided to Overton matches the data record, and also how to tune the parameters in Overton. So in this example, which was an LP task involving identification of parts of speech, intent, and the arguments of an intent, and also entities, the user provides a payload with inputs, which are in this case tokens, query tokens, the entire query itself, and the identified entities. And the task provides with supervision. Tasks provides with supervision, for instance, parts of speech, the entities, and the intent and the argument of that intent. If you look at the schema, it basically matches one-on-one with the structure of the data. And you can see that what can be specified is the payload with each single entry in the data record matched, and with data types, for instance. Tokens are treated as sequence, the query is treated as a singleton, and the entities are treated as a set. And also for the tasks, each of them is treated differently. Like, for instance, for parts of speech, there's a multi-class classification happening. For the entity type, there is like a bit vector because it's a set of elements. For intent, there is a multi-class, and for the intent arguments is again a multi-class. This provides a structure for the definition of the models that needs to be trained, but the tuning part is what provides the optional options that the system tries and tests out. For instance, in this case, for the tokens, there's a set of options for the embeddings, for how to encode them, and for the size of those embeddings. And the same is true for other for information about the other payload elements. So in particular, the schema and the tuning are the part that the user needs to specify. They are easy to read, much more easy to write compared to writing your machine learning code from scratch. Touching on Ludwig, which has been developed in a way that is independent of Overton, but actually ended up having a lot of similarities with Overton, and that's why we're talking about them at the same time. Ludwig is an open source project backed by the Linux Foundation, and it's a low-code declarative framework for building deep learning networks. And it supports multitask learning and mixed modalities sorry, let me repeat this part. So Ludwig is a system that has been developed at Uber and used in production at Uber, and had many similarities with Overton, despite having been developed in a way that is completely independent. It is open source and supported by the Linux Foundation, and basically provides a low-code declarative interface for building deep neural networks. And it supports multitask learning and multiple modalities. It has more than 8,000 stars on GitHub and many downloads a month and many contributors. It is based on an opinionated assumption on the architecture of the underlying model. This architecture is called ECD, for encoder combiner decoder. The way it works is that users can specify many inputs of many different data types: categories, numerical, binary, text, image, audio. And associated with them, there's pre-processing functions and encoding functions that map raw data into tensors that are, again, dependent on the different data types. The information from all these different inputs is combined by a combiner module that provides then tensors as inputs to the decoders that, depending on the different task, can perform different operations. In particular, for category, there's multi-class classification. For numerical, there's regression. For binary, there's binary classification, and so on and so on. And so the decoder produces the predictions, and they are post-processed back into the data space. The nice thing about this architecture is that it is very flexible, and different instantiation can solve many different machine learning problems. For instance, if you have many different categorical, numerical, and binary features as input and numerical feature as output, then you are basically performing a regression task. If you have text as input and category as output, you're performing a multi-class classification of text multi-class classification. If you want to do image captioning, you just specify an image as input and text as output. And the same is true for speech identification, forecasting, and binary classification, and many more tasks that you can just imagine are just a combination of inputs and outputs, really. And so models can be specified as configurations in a way that is kind of similar to Overton. In this case, you just specify input features and output features, and for each feature, you specify the data type, being it text, category, image in this case, or set and numerical for the outputs in this case. And this is all you need to specify. But if you want to, and defaults will be used in this case for determining the actual parameters of the system, the architecture, and the training parameters. But you have also full control all the way down to the low-level details of the architecture, the number of layers, the pre-processing, the tokenization, as you can see here. You can encode text with BERT, for instance. You can encode categories with embeddings, and which encoder to use for images like ResNet. And you also have control over all the training parameters, the optimizer, the learning rate, the epochs, and also you can declare the hyperopt parameters that you care about, in this case, the number of layers and the learning rate, and they will all be optimized for you by the system. Moreover, it's very easy to use also programmatically. You just have to do pip install Ludwig in your Python environment, and there's one line for importing the model, one line for instantiating it with a specific configuration, one line for training, and one line for predicting. Serving a model is also very easy. There's just simple Ludwig serve command, and you specify the path of the model that you trained before. So by developing these systems, we actually learned some lessons that we believe could be useful also for other people implementing systems in the future. In particular, we realized that we can increase the number of users by providing higher level abstractions, and basically they are needed to be developed for making people able to develop machine learning, use machine learning without coding skills. We believe that basically we're still in the call era of machine learning, that we want to move towards a SQL era of machine learning. Regarding performance optimization, usually abstract systems tend to make compromises, either in terms of expressiveness or performance. Overton and Ludwig suggest that this may be a false trade-off, because they can achieve really high performance and be super useful in production, and having a really small to zero compromise in terms of expressiveness too. We also realize that explicit user roles are very important. In particular, not everyone interacting with the system needs to be trained in machine learning, statistics, or computer science. And people providing supervision in the case of Overton didn't need to have any understanding of that. And so this separation of interest, and we need to have even more of that, this separation of interest is what made it possible. And finally, we witnessed this symbiotic relationship between systems and libraries. And we believe that there will be even more libraries in the future, and they will coexist with machine learning systems in a virtuous cycle, because both these systems, Ludwig and Horobot, are built on top of TensorFlow and PyTorch. So there's a really virtuous cycle going on there. To conclude, what we believe is next for machine learning systems and declarative machine learning systems. In particular, recent work in deep learning has suggested that the architectures may not be so impactful in terms of performance as compared to data volume and quality, in particular for large learning models. And so we believe that there's a huge value to untap in bridging the gap with data-centric approaches with the more modeling and centric approaches. And we also believe that higher level systems in the future will seamlessly integrate model training, inference, and data aspects all in one place. In particular, we are building right now such a system, and we are calling it Predibase. And if you're interested about knowing more about it, please feel free to reach out to me at piero@predibase.com. I want to close this presentation by telling you that we believe that technologies that change the world only do that when they can be used by more people than those who can build them, and that we believe that the future of machine learning and its impact on everybody's life depends heavily on putting it in the hands of the rest of us. Thank you very much for your attention.